Okay. But in the past, we had mechanical energy. Well, you guys remember conservation of energy? I know it's been a while for us. I hate these, it's fine. The conservation of energy looks something like um, delta and E equals 0. So that means that M E initial equals M E final. And E was comprised of potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. So this was the conservation of energy. Okay, cool. Well, springs have a different form of potential. So the potential energy due to a spring is defined as PE spring, PES, is equal to 1/2 K x squared, with K being our spring constant and X being the displacement. Okay. And the way to think about this, because this should be kind of intuitive, is put it up spring like this. Yeah? We'll hang it up. The more that I stretch the spring, the more potential it has. What does that mean? It means that I'm storing energy, right? So here I'm storing quite a bit of energy. If I release it, it's probably gonna fall off here next time, which I'm not particularly fond of. So we're not gonna do that. But stretching it like this has less energy, less potential than if I stretch it all the way like this. And you know intuitively that that's true. Not only is the force gonna be stronger because X is larger, but we are also storing more energy. Not only that, but if you remember, work is equal to mgh. So mg, the gravitational force, multiplied by the distance. So that means that by just increasing the stretch length, we are also increasing the potential energy. Very cool. Kind of curious, right? They definitely do take a little jump. Okay. Cool, cool, cool. So the potential energy or the energy stored in a spring depends on two factors. One, how stiff is the spring? If you've got a very stiff spring, then even a tiny amount of displacement results in a lot of energy. Like, for example, the shocks on your car, those are really stiff, like really, really stiff. And so when you are driving, Even a small displacement results in a huge force, keeping the rest of your car up. Right, that's kind of their whole point. So those springs have to be stiff because you don't want those springs compressing just normally, right? They have to experience a force, which happens when you like fall in a hole or something like that. When you fall in a hole, suddenly you gain some energy that compresses the springs, and then the springs, because they store so much energy, push your car up, resulting in a smooth ride for you. Okay, cool. So we can rewrite our conservation of energy formula to include the spring force. So we're just gonna add one more term to our equation of, I can't spell, initial plus PE from the spring initial plus kinetic energy initial. That all equals potential energy due to gravity final plus PE from the spring final plus KP final. This is gravitational potential energy. That's that MGH1. This is potential due to a spring. That is PES equals 1/2 kx squared. Finally, I have poor flying skills. My apologies. This, whoops, this is kinetic energy, and it's equal to 1/2 mass and velocity squared. And so we just end up with a slightly longer formula. Now, in all of the problems that we had before today, did any of them have springs? They did. So did you have potential due to a spring? You did not. So that means that that term could have been there. It was to zero. But does this really change the way that you handle this formula though? Not really. You're just adding more stuff. So instead of two terms, then you have three. Instead of two numbers, then you have three numbers. Is that significantly harder? Not really. Okay. Also, just so you know, PEF is a conservative. So here, this is the work done by non-conservative forces. This is like if you have friction, air resistance, but PES itself is conservative, just like PE is conservative. KE is also conservative. Okay, so here, imagine you have a block that is sliding towards a unstretched, uncompressed spring. So you've got this block and it's moving towards it. Do you have right now, before the collision, right? Do you have potential energy due to gravity? No. Why? You can't fall, right? H is 0. Okay. Do you have potential due to a spring? No. Potential due to a spring depends on compression of the spring. Are you compressed? No. Do you have kinetic energy? Sure. There's lots. So the only energy that you have in this scenario right now is kinetic energy. So all you have is 1/2 mass and velocity, right? Okay. Cool. Now let's say that we advance time just very, very briefly, and we are at this point. Okay, so this block has now made contact with the spring. This is an ideal spring, which means that its mass is 0, which means that the kinetic energy of the spring is negligible. We don't care about it. It's gonna sit at 0. That means that now the total energy of the system is however much energy the block still has for moving, plus the potential energy from the spring. Right, because as soon as this block stops moving, what is the spring going to do? Let's launch it back. Yeah. So that must mean that we are storing energy in the spring. We are converting that from kinetic energy of the block to potential energy in the spring, just like we were converting between gravitational potential and kinetic energy. Same idea, same deal. That's what I'm telling you. If you felt okay handling conservation of energy problems before, this doesn't really change it. It just adds one more term, but so what? It just means that you have slightly more algebra to deal with, but that doesn't significantly change the approach. The approach remains the same, which is helpful because it means that you can keep, well, you can keep that same scaffolding, all the stuff that you learned in the energy unit. That's all still the same stuff. If you get stuck, you can always reference earlier material because conservation of energy works the exact same way now as it did then. Okay. Okay. Now here, the block stops for just one instant. That means that the kinetic energy of the block is now 0. Why? Because velocity is 0. And all of the energy is now stored in the spring. What's going to happen 1 second after? It's going to get heated, huh? Yeah. One important thing to note here is that the total energy of the system is going to stay constant. So that means that if the block before contact, if that block had 100 joules of energy, all in kinetic, at this point, we have 100 joules of energy, but stored in the spring. So the total amount of energy is the same. It has to be, right? That's what conservation of energy. You can change between the types of energy, but the total amount, the numerical value, has to stay the same. Okay. But right now, the potential energy is entirely in the spring, and we know that once that spring expands, so it was compressed this way. So what direction is the force that the spring is going to emit? That way. Remember, it's always opposite of the compression. Okay. Okay. And as soon as this block gets heated, it's going to regain all of its kinetic energy. Because it had 100 to begin with. It changed it to potential. Then all of that potential was then again swapped to kinetic. The amounts have to be the same, or else energy wouldn't be conserved. And because these are all conservative forces, energy must be. Okay. Cool. Cool, cool. Okay. Well, that means that. We did put salt, we did energy. You don't actually go super hard in terms of deduction. You will be working with pendulum. But, okay. Let me introduce the next topic, and then we'll go. I don't have a problem. Okay. So we actually already met all of our goals for today. The next section is actually randomly on fluid. So, fluid. So what is a fluid? This is a material that can float. What does that mean? It means that liquids and gases can be fluid. Okay. Actually, actually, just kidding. We're gonna end here. I kind of need the pictures. I should have like pictures. I don't have. So we're gonna stop here. We did have turned the cover and entire chapter, so then remember, live on Wednesday, please show up. It'll be on screen. Have a nice rest of your day. Canvas is down. Once it's back up, I will open up the labs again.